When an Amazon warehouse robot crosses a 1,000,000 square foot floor without colliding, it's not magic, it's metric multiplication. Today we will show how Chapter 8.1, the same math in our STQM1223 syllabus, drives the world's largest fleet of warehouse robots. Identify the topic and chosen application.
Mathematical foundations of linear transformations. Definition and key properties. A transformation T is linear if Tu plus V equals Tu plus Tv and Tcu equals Ctu for all vectors u, v, and a scalar c. A critical consequence is T0 equals 0. The zero vector must map to 0. Translation violates this property, proving it is not a linear transformation in R squared. Standard metric representation. Every linear transformation T, R to N maps to R to M, can be expressed as Tx equals Ax, where A is an M by N metric. The columns of A are determined by the images of the standard basis vectors TEI. Column 2D transformations, rotation, scaling, reflection, and shear each have a distinct standard metric form. Common 2D transformation metrics. Every linear transformation T R squared to R squared can be represented as a metric multiplication Tx equals Rx. The columns of A are determined by where the standard basis vectors E1 and E2 are mapped. Below are the 4 essential 2D transformation metrics used in robotics and path planning.
Quick proof of 0 is not equal to 0 for translation. Introduce 3 by 3 SU2 form. State composition theory, where composition equals metric product, and know that this operation is non-commutative.
Robot path planning process. Define robot pose, represent the robot's position and orientation as x, y, theta in the warehouse coordinate frame. Convert to SE2 matrix. Encode each pose as a 3 by 3 homogeneous matrix combining rotation and translation in a single operation. Multiply transformations. Train each motion step by multiplying SE2 matrix. Rotate then translate, or translate then rotate. Compute T-path. Final path equals T0, delta T1, delta T2, delta Tn. Each matrix multiplication updates the robot's pose on the grid.
1 million drive units across more than 300 facilities. A 1 meter condition grid covered with barcoded shakers. Every forward 1 cell or rotate 90 degrees, command is represented by an SE2 matrix. The entire path is a product of Tn through T1. And the system achieved a 25% productivity gain in shipport, and reduced the click-to-ship time from 60 to 75 minutes down to 15 minutes. An important note: A star decides which cells to move through, while linear algebra describes where the robot actually is.
Rotate then translate. Steps 1 to 2. Vase translate then rotate. Step 3. Starting from 210 degrees. Show all arithmetic. 210 degrees order matters. No communicativity in robot path planning. Starting pose 210 degrees. The same start. 2 different sequences. 2 different outcomes. Rotate 90 degrees CCW first. Then move forward 3 units. Robot ends at 2-4. Move forward 3 units first, then rotate 19 degrees CCW. Robot ends at 5-1. Conclusion: AB not equal to BA. Matrix multiplication is non-commutative and in robotics, the order of operations determines where you end up.
The same metrics you learn in Chapter 8.1 are running in real time across 1 million robots worldwide. And thank you for listening.